210, right? 210 degrees. 210 degrees from a 0 going across or around us in a particular direction, and then elevation of 30 degrees to go up this way, and then an R value of like 3 feet to reach out. So that is a unique location in space. Yeah. And the interesting thing is, the more you start looking at all of these things, the more you start thinking about it, like the more meta your knowledge becomes. So this one actually is spherical. So it's a kind of polar coordinates, but it's not. It doesn't limit itself to 2 dimensions, because we're adding this bearing in addition to, I guess technically we're adding elevation, and phi is our, yeah, whatever, it's fine. So there's also another one called cylindrical coordinates, which use r and theta, but then they use z. So you go around, pick a distance, and then just go up a certain distance. Yeah, so you're looking basically on a cylinder as far as where am I looking. So my origin is here. I have a radius which gets me out to the edge of the cylinder. I have a an angle which tells me what bearing I'm at, and then I have a z. You know what? Let's not do that one. And then I have a z which tells me how high I need to go. So again, like along the bottom here is going to be that phi. So what bearing is it? Yeah, and they're of variable size depending on what your values are. So, you know, you don't have to, it doesn't have to be a fixed cylinder or a fixed sphere. Your R value is going to change the size of that thing. And it's real fun when all 3 of them are variables, because that just starts doing all sorts of crazy stuff. Yeah, I meant to actually type this out. So Stephen Baxter and Terry Pratchett wrote a book series called The Long Earth, which surprisingly kind of allowed me to understand 4-dimensional space a lot easier. The major idea behind the book is that Earth is not actually alone in terms of like space. Basically what happens is somebody develops a box which is run on a potato. So they create like a potato battery basically. And then it hooks up to some little device, and it's a black box. It doesn't matter what it is, but it's called a stepper, and somebody accidentally like stepped out of our Earth and ended up on a different Earth. It is almost identical in almost every single way. It is ever so slightly different. One, the major difference is there are no people anywhere. Like, no people at all. So they're like, oh, well, once they figure out that they can come back, they're like, huh, well, this is really nice, because now we can just, like, go there instead of living here on this crappy planet. So a whole bunch of people, like, decide they're basically going to become settlers in this new dimension. And so they step over to the next Earth. And then when that one starts getting crowded, they're like, oh, screw this, and step again to the next Earth, and step again to the next Earth, and step again to the next Earth. And some people are like, all right, we're just going to become explorers and decide to step as far as they can to get away from other people and stuff like that. Oh, not even like never explored space. There are no people. So like in oh, I see. I see where you're going with that. Well, sort of. So as people start stepping out further and further away from Earth Prime, um, they start noticing that there are slight differences. So like objects that were in the same place in our Earth are not in the same place as other Earths. They're slightly off in the next Earth over, and slightly more off in the next Earth over, and slightly more off in the next Earth over. Or in some cases, like, pockets of iron or gold or stuff like that end up like going from this place to in the next step over, they're actually smaller. And in the next step over, they're smaller. And the next step over, they're gone. And it's like minuscule changes, but they add up. And so this four-dimensional space starts showing up that, like, if it were a sphere of, it's not how it works, but whatever. If there's a sphere of iron deposit on our Earth, then on the next one over, it's like a slightly smaller sphere and a slightly smaller sphere and a slightly smaller sphere until it eventually shrinks down to nothing. So this is a four-dimensional sphere. The steps are also incremental, which is different from like how actual 4D space works, where it's actually continuous. But whatever, it's fine. And then so the main character ends up going on the expedition to like find the farthest reaches of stepping. They create a boat which is able to do like 100 steps a second or 100 steps a minute or something like that, and so they just keep stepping over and over and over again. And there's some just interesting stuff that they figure out. One of the major problems that exists is that anything that is made out of iron doesn't step. So like, people will be wearing clothing and it's fine, but if they bring a pickaxe with them, like on the other side, there's no head. It just kind of like they stepped and it fell to the ground. So there's no way to bring iron back and forth between the worlds, but they can also bring other stuff like gold. So some people were like, yeah, I'm gonna go get gold and bring it back, or platinum or whatever, and then like the price of that stuff on Earth Prime just plummets because the supply is in there's so much of a supply that like nobody cares anymore. The only thing that actually is limited is iron. And it's not completely, like, it's not like the price doesn't skyrocket because there's the same amount of iron here as there always was, and you can't get more of it from anywhere else except maybe like space. But then basically Earth Prime starts thinning out and there's fewer people. I mean, arbitrary in the sense that it was plot convenient. But I think that they explain it away by saying like iron is also the element that neutron stars will collapse down into, and like as soon as all fuel starts collapsing into iron, like that's it. It can't go any further. There's no way to crush. There's no way to fuse any element heavier than iron in like standard fusion. The only way to get heavier elements, so like uranium or plutonium or any of that stuff, californium, all that stuff that's lower down than iron on the periodic table. Even like I don't remember if it's barium, but one of them, even stuff that's not that much further down on the periodic table. the only way to get any of those is through um, hyperfusion, which occurs in supernovas or supernovae. Iron. Huh. Yeah, okay. So even like cobalt, nickel, copper, zinc, like that stuff doesn't exist unless it forms inside of a inside of a supernova. Yeah, I mean, so a supernova will rebound all of that material. So it crushes everything down into all of these super heavy elements and then blows them out off into space. And then whatever happens inside the black hole, we have absolutely no idea. Eventually, all of the material in it starts getting evaporated off via Hawking radiation. But I mean, that takes eons to actually end up doing. So Stephen Hawking first theorized that there was this radiation that was coming off of black holes, which would eventually start sapping some of the energy from black holes. And I don't remember. There's a lot more to it, but yes, as in electromagnetic radiation. Now, I think it had to do originally with like quantum entanglement of two particles that appear right at the event horizon, which, like, it's practically nil, but it still happens because it's so large. And so it can still radiate. It just can't send out. No, I mean, that's a good question. It's been years since I've read my copy of. I'm probably due for a reread. Okay, yeah. So that's how it works. So all around the event horizon, there are particles that are being created through the 0 point energy, right? So if you've ever heard of 0 point energy, it's just basically two particles get created, a particle and an antiparticle, and then they come back together. And this is happening like all the time in the quantum foam. Or they call it the quantum foam because basically there's all around us, there's just particles that are hissing into existence and out of existence, like on an instantaneous basis, all the time. And right around the event horizon of a black hole, this is also happening. But the thing is that if they separate and one of them drops into the black hole, the other one is then free to leave, and it doesn't come back together. Like some of them possibly do, where they could, like the one around the event horizon could then fall back in. And I don't know if it would eventually meet its partner, but it would probably meet a partner. So, so the quantum foam was actually discovered. Plates. Who did the plates? There was an experiment where there were two plates that were put really, really, really close together, like closer than I could possibly put my hands together. And basically, you've got the same quantum particles that are created and then destroyed almost instantaneously, all over the place. And on the inside of these plates, it's happening less often because there's less space inside of it, but on the outside there's more of it happening. And so, like, because of that, it creates a pressure differential. It's so minuscule that it's ridiculous to even think of it as a pressure differential. But because of this idea, they were able to actually put plates that close together and measure the vacuum energy that sucked the two plates together, the pressure differential that existed in the quantum foam. I mean, it's ridiculous. I know. It's ridiculous. So I was actually like on the path to becoming a theoretical astrophysicist, and this is kind of the idea, is that like you just read all of the papers that everybody has done before you, and you just start like spitballing ideas around that are like, what if we did this? You know, one of them was like, you could actually get a well, really, I mean, the major problem with almost all of it is how do you then control for all of the other vacuum energy that could exist around you? So, like, you know, just air particles, or even at that point, you could even think like, you know, photon pressure could potentially be throwing stuff off. So, like, you know, how do you, how do you isolate everything and then make sure that the only possible way for this to happen, for these plates to like smack together, is from the quantum foam, if it exists in the first place? And yeah, I mean, I don't pretend to know either. I'm an armchair astrophysicist at this point. I have read almost all of Stephen Hawking's books, but that's as far as I've gone. So in theory, yes, but at, you know, in practical terms, probably not. As if you're looking at the like gravity of stars that are all around us, one probably probably it's going to be more or less canceled out because you have enough stars in every direction that they're more or less going to cancel out. And the gravitational effect drops off by the square of the distance. So if you're talking like, you know, the gravitational energy is that gmm over d squared. So if d is like in terms of light years, then you're talking squares of light years in the denominator. So like the gravity from my body would probably affect this experiment more than any star other than our own. And that's also something you'd have to control for, is like, what about the gravity, like what about the gravitational effect of like the apparatus itself? I mean, yes, it is inaccurate because of quantum physics. um, gmm over d squared is good enough when you start talking about you know, general physics. When you start talking about the fact that we're in a like moving frame of reference, then it starts getting into general relativity. And if we're moving very fast or around very heavy objects, then we start talking about special relativity. And yeah, it alters that, but again, on a minuscule level. So then you've got to say, okay, how does it affect, how much does it affect it on that minuscule level? And that's where most of these experiments come from. In terms of books, I would recommend Bill Bryson. I think this is the name of the book. Let me just double check real quick. A Brief History of Nearly Everything. Yep. So this has an overview of like a lot of the Einsteinian, Newtonian, Hawking, Hawkingian, um, physics that have been created in the last, well, in pretty much all of human history. It starts from the very beginning of human history and starts developing like, what have we learned in science? And it gets into more modern stuff. He wrote that in like 2000s, so it's it's pretty up to date. There is stuff that has been done in the last 15 years ish, which has, possibly changed his book, but not a huge amount. Because again, a lot of it is like, here's the historical context, and then here's where we are now. And it's like a very brief, here's where we are now. So some of that here's where we are now stuff might have changed slightly, but let's be honest, it hasn't changed that much in 15 years. With the exception of like Higgs boson, the discovery of the potential particle for carrying gravitational forces and gravitational waves. The discovery of gravitational waves in 2012, 13, whatever it was another like major shift within physics. But at the same time, it's like, well, that kind of only affects people who are like in that area. Generally speaking, it doesn't make a huge fundamental shift of like all of physics, like the invention of calculus, right? The invention of calculus by both Newton and Leibniz, that like shifted everything, changed everything on the face of the planet. And who's it? Edmund Halley, like developed the equations to discover when Halley's comet was going to come back every single time, and figure out its actual orbital path, like orbital trajectory. I mean, yes and no, because I mean the physics that's here, right? It's just basically the application of the mathematics and seeing how accurate the mathematics is in terms of all this other stuff. So it doesn't always work 100%. And the math is only as good as the operator. So all this stuff that I did up here, right, with all this like work equation, things like that, like technically these are correct. But again, one could argue that like this surface area never actually exists. It's just a theoretical value. I don't have any sort of shape that could be made perfectly into this. And even if I got a 3D printer, which was the most accurate thing that I could possibly get, I'm never going to create something that's this perfect. I mean, it might be that perfect because that is a terrible drawing, but nonetheless. So am I a Platonist, basically, is what you're saying. Uh, I think that theoretical objects are a theoretical maxim, but I don't necessarily think that they are, like, objects unto themselves. I think we can create approximations of them. Like, physically, we can create approximations. You try to draw a line on a paper, well, it's not really a line, even no matter how straight your ruler is, no matter how exact it is. Even if you, like, laser cut a line, it is still not a line. I mean, apart from the fact that it has depth. And width to it, right? So, even if it were like that, like, there's technically no such thing as a one-dimensional object. The Flatlanders run into a few problems in which, like, right, and zooming in, it should look identical to where you just were. I mean, nowadays we can create literal one-dimensional lines. I mean, it's again not exactly that because when you draw it on the screen, it has width to it. But again, um, in the sense that if you zoom in, it looks identical to what you just had, you can actually draw a line on some graphing utility. And when you zoom into a line, it is still a line. It is still of the same width. It is still of the same depth. Yeah, you're getting into like of physical matter, yes, ish. I think the true answer is we don't know yet if there is something even more fundamental than these. Electrons and quarks technically are as fundamental as they get at the moment, but like until we can actually observe anything smaller or more fundamental, then yeah. I mean, I if you want to get into technical ideals, like energy, raw energy is like the fundamental. And I think somebody, I mean, Bill Hicks, and there was a old joke that he did about what was it? Today, young men on acid realize that all of existence is just energy slowed, energy. No, I forget the words, but what genre? Oh, sure, go for it. All right, got any in mind? Sorry, what? Did you try to post a link? Yeah, all I see are 3 asterisks. I don't know if I blocked it. I don't think I did. I mean, like, I didn't choose to block it, but... Did I not update my stream information? Does it still say, like... No, I did. Okay. Anyway. Yeah, I don't think I don't think I set that, so that's probably just a default. Um... That's not what I want. Meet to October 31st, 2020. All right. I'm in. Any particular event? Oh, right, logic.